All right, thanks so much for organizing this wonderful workshop again and for having me. I'll get right to it. Okay, it still doesn't work. That's okay. Go it this way. Here's the outline. Talk will have three parts, and I'll start with the first one. I'll review the Penrose Singularity Theorem and the modification of it by Aaron Wall, and describe some of the limitations and why we would like to do better. The motivation, of course, for the Penrose Singularity Theorem, 1965, got a Nobel Prize, is that you would like to know whether the singularities that we see in the exact known black hole solutions are in fact generic, or whether they are an artifact of the high degree of symmetry that one has to assume in order to find any exact solutions at all. And you can't really solve this or answer this question numerically because perturbations, for example, go out of control in gravitational collapse. Intuitively, it's not so clear in Newtonian gravity, for example, if you have particles that are not exactly symmetrically arranged, they sort of miss each other and fly back out. And so this was the huge advance of Penrose's theorem that it proved genericity of singularities. Let me just quickly review how that proof goes. So we're assuming that we have a spacetime which is globally hyperbolic and not inextendable. And it has a non-compact partial Cauchy slice, which I'm showing here with this blue wiggly line. Non-compact here sort of intuitively means it goes off to infinity somehow, right? And this Cauchy slice has a trapped edge, which I'm showing with a blue dot. Trapped means that this edge is a compact codimension 2 surface, and that the null generators of the future Cauchy horizon H plus A that are coming out of that edge, that those light rays have negative expansion. That's what trapped means. It's not exactly the definition that Penrose used, but it's the one that will be more convenient for going forward. So with those assumptions, and one more key assumption, namely that the spacetime M satisfies the null curvature condition, that a Ricci tensor twice contracted with any null vector is not negative, then the spacetime is singular, and the technical definition of singular that Penrose used is that of null geodesic incompleteness. That means that you have a null geodesic which goes on for a finite affine time and then cannot be continued further. It just like ends. And that's a nice definition, both physically and also because you can prove this result. And you see here this is a null geodesic that ends on the singularity. How do you prove this? Well, you prove it by contradiction. You assume null geodesic completeness. And you observe that when you have a partial Cauchy slice that's non-compact, then its future Cauchy horizon cannot be compact. So here's an example where I have a partial Cauchy slice that is compact, this disk. And then, of course, this future Cauchy horizon, the cone, is allowed to be compact, makes perfect sense. Now, what's happening here is that if you assume null geodesic completeness, then the fact that those light rays coming out of this edge have negative expansion tells you that the future Cauchy horizon actually looks like this. All the light rays have to intersect each other and leave the future Cauchy horizon within a finite affine time. This is guaranteed by the classical focusing theorem, and that's where the null curvature condition is being used. Okay, and of course that's precisely the contradiction that we wanted. Non-compactness of H plus of the Cauchy horizon would have required that not all of the null generators leave after finite affine time. All right, so again, a key thing here is that Penrose's condition, trappedness, and the existence of this trapped surface, or trapped edge, is easy to verify numerically or in perturbation theory. It's something that you can easily see is generic. If you have a spherically symmetric solution, you perturb it a little bit, you had some trapped surface deep inside a black hole, it's still going to be trapped. And then I should emphasize the theorem can, of course, be time reversed. So if you have a non-compact spatial slice in your cosmology, and there's an anti-trapped surface outside of which there's infinite spatial, non-compact spatial region, then the theorem predicts a past singularity. I will not talk about this today, but I just want to mention that this non-compactness assumption is a little bit annoying because we don't really know whether our universe is closed on distance scales much greater than the visible universe. But it can actually be eliminated if the covariant entropy bound is assumed. But again, that's not the direction that I'm going to pursue today. So what does this theorem do for us? It completely settles this question of genericity. And that's great. But it does not settle the physical question of whether our past had a bounce, whether baby universes can appear inside a black hole by just some kind of semi-classical evolution. It doesn't settle that question because the null curvature condition is known to be false in nature. That condition is equivalent in Einstein gravity to the null energy condition. Stress tensor twice contracted with the null vector is greater than or equal to 0. And any relativistic quantum field theory has states for which this is violated, including the standard model, of course. Now, this might seem a little contrived. I mean, what are the chances that in some generic gravitational collapse, we're suddenly going to find the null energy condition violated in just such a way that we're avoiding these conclusions of Penrose's theorem? But it's actually not as conspiratorial as it sounds. When you think about another theorem that was proven around that time, Hawking's area theorem, which also assumes the null energy condition. And you might have said, well, okay, what are the chances that near a black hole, the null energy condition is always violated so that the area does shrink after all? Well, that's exactly what happens, right? And so you could be of a mindset where you say, okay, this theorem has no physical relevance. It could very easily be overridden by just null energy condition violations being generic in gravitational collapse. And so from this point of view, I have no justification to complain about the cottage industry that has been going on for the last many decades, where people keep inventing bouncing cosmologies, cyclic models, baby universes sprouting from the interior of black holes. They are not ruled out as physical possibilities by the Penrose theorem. So that gets us to Wall's improvement. Well, we'll see in which ways it's an improvement and which ways it's worse. But so Aaron Wall had what seemed to me at first a totally counterintuitive idea that you can eliminate this problematic null energy condition, which we know is false, and replace it by the generalized second law of thermodynamics, which has at least, I mean, we don't know that it's false. It has a chance of being true. And if it's not true, it's unclear what the ordinary second law of thermodynamics still means. So it's a much more solid foundation than one which we already know is wrong. So what is this generalized second law? Just to briefly review it, it applies to causal horizons, we believe. A causal horizon is the boundary of the past of a subset of future infinity. So that could be a Rindler horizon, a black hole horizon, de Sitter horizon. And the generalized entropy is of course given by the area of this horizon plus the von Neumann entropy of the quantum fields outside of it, plus higher curvature corrections that we'll come back to at some point. The GSL can also, which of course was invented in the context of black hole horizons by Bekenstein, can also be viewed as a quantum corrected area theorem. So whichever way you state it, either you say that the generalized entropy can only increase or stay constant with time, or you could have said that this quantum corrected area can only increase or stay constant with time. I've suppressed H bar, I think, in most places, but of course there's really an H bar here, so it's quantum correction. All right, so what does Wall's theorem say? I've sort of tried to highlight what's changed compared to Penrose's theorem. Okay, so the first thing that changes is that you, in the assumptions, you trade trapped for quantum trapped. That's just a statement that instead of assuming that the area decreases under small deformations of this edge sphere here along H plus, the future Cauchy horizon. So trap means that the area decreases under small deformations up that way, right? Quantum trap just means that under all small deformations, the generalized entropy decreases when you deform this edge up along these light rays. Then instead, as promised, instead of assuming the null curvature condition, you assume the GSL. Conclusion remains the same. One of these generators is incomplete. Proof goes as follows. I'm actually going to give you a warm-up proof, which is effectively just, again, the proof of the Penrose theorem, a classical version. But we'll prove it from Hawking's area theorem instead of proving it from the null energy condition directly. And that's useful because then the step of going from Hawking's area theorem as the assumption to the GSL as the assumption, those are two very closely related things. It'll be easier to take that step later. So again, we assume the first part is kind of the same. Assume null geodesic completeness for contradiction. H plus cannot be compact because this Cauchy slice here is non-compact. Therefore, again, it can't be true what's drawn here with this cone situation that all of the null generators, these red lines of H plus, leave H plus after a finite affine time. At least one of these generators has to keep going. So here it is also shown, hypothetically going for an infinite amount of affine time, which means it reaches Scri plus. Scri plus is sort of by definition the endpoint of infinitely long null geodesics. And so it connects this edge of the region A. There's some point on that edge which is connected to a point Q on future infinity. Okay. And now we can use that point Q to define a causal horizon. In other words, look at the causal past of Q and the boundary of it. Okay, and that boundary by causality is going to lie in, it's going to intersect this global Cauchy slice somewhere in the region sigma A in that partial Cauchy slice. And it's also going to touch P because this is a sort of unbroken null geodesic. Okay. Now, by the area theorem, we know that the light rays coming out of that causal horizon, despite what it looks like on the picture, the light rays going off towards the future and the right in the picture, those light rays must be expanding or else the area theorem would be false. So I've tried to draw this again with my limited abilities, but here they look, it looks more like they're actually expanding. Okay, so again, the orange thing is how the causal horizon intersects this Cauchy slice. And just by basic geometry, you can immediately see, right, that locally this edge of A, which is this line, is obtained by bending this Cauchy horizon outwards, and that just makes the expansion even more positive. Okay, you can see that those light rays are going to be expanding more rapidly away from each other, the ones coming out of the blue surface, compared to the ones out of the orange surface. So this is, you can make this mathematically rigorous, but hopefully it's sort of intuitively, in this case, your intuition is a good indicator of what happens. And of course, now we have our contradiction because we wanted to assume that this edge is trapped, so it had to have negative expansion going up. Okay, so now we're ready to switch over to the full quantum version of Wall's theorem. And of course, the first parts of the story are the same. And now we're going to say, well, by the GSL instead of the area theorem, the quantum expansion instead of the classical expansion of these orange light rays coming out of the causal horizon C, or making up that causal horizon, have to be positive. And we'd like to argue again that means that the quantum expansion of the blue light rays has to be even more positive. And that's where you hit a bit of a bump in the road. The classical part of the story, of course, made perfect sense. Your intuition was right. The classical expansion has to be bigger when the light rays come from this bent out surface. But it's hard to compare the variations of the von Neumann entropy, of the quantum correction to the area, between these two deformations. I've just drawn two generic surfaces here, and they touch in the way that I showed earlier. And when you deform them, the sort of amount by which you reduce the region, these shaded regions here that come from the deformation along the light rays, are just not the same. So the deformations are not related to each other in any obvious way, and that makes it difficult to compare how the rate of change of the von Neumann entropy compares between deformations of A and deformations of B. All right. And Wall's resolution to this obstruction, which he called the touching lemma, was to take the limit as G Newton goes to 0. Okay? And in that limit, either you're in a situation like this, where the surfaces have different classical expansion, and in that limit, the classical expansion dominates, and so you can just use the classical argument that's very intuitive that we already discussed, and you're done. You don't have to worry about the von Neumann entropy variations. And there's kind of an intermediate possibility that I'm omitting for brevity, but he thought about it. The two surfaces coincide in some open neighborhood, not just at one point, but in some whole open neighborhood, in which case you can, of course, find small deformations that are exactly the same, that access exactly the same region, no matter whether you start by deforming A or B. You just make them small enough that they start from this open neighborhood where they coincide. And then, I'm not going to derive it in detail, but it turns out that strong subadditivity works in the right way, and you can again show that, so in this case, the classical expansions are identical, so the only thing that matters is how do the variations of the von Neumann entropy compare, and it goes the right way, and we're done. Okay, so why are we not happy? I have two sort of complaints about this, or reasons to feel not completely satisfied about this G goes to 0 limit appearing in the proof. Okay. One is that we frequently, and in recent years more frequently, encounter situations where the quantum and classical expansions are actually almost balanced or completely balanced against each other. Right? The sort of key example is, of course, a quantum extremal surface that bounds an island, an entanglement island in an evaporating black hole. The classical expansion in this direction is perfectly large, but there's a quantum expansion that is equal and opposite. And in situations like this, you can't take G to 0 without completely destroying the setup. The other complaint, and nearby, of course, nearby this quantum extremal surface, there are quantum trapped surfaces for which the two contributions still almost exactly cancel. And you'd like to be able to apply the singularity theorem to this quantum trapped surface, but again, we can't. The second objection is one that I learned about from Edward Witten, which is that anytime you have a perturbative argument for a singularity theorem, you should worry that you might get false positives. Suppose the Ricci scalar goes like this. So T is the proper time along, let's say, a time-like world line. And there is no singularity here. It's resolved by this term here proportional to G Newton. But in a perturbative expansion in G Newton, you would not see that. Every term in the expansion is singular at T equals 0. In fact, it just gets worse as you go to higher orders. So to be certain that the singularity that your theorem predicts is real and not just an artifact of a perturbative expansion, you would like a non-perturbative singularity theorem. That was so great about Penrose's theorem. It's non-perturbative. So let me just summarize the limitations. They're sort of different. Penrose's theorem is non-perturbative, but classical, it makes an assumption we know to be false, the null curvature condition. The Wall theorem is semi-classical. It starts from the generalized second law, which might actually be true, but it's perturbative. If we want to stay with the generalized second law as our starting point, we sort of want to work in semi-classical gravity, then we have to worry that we might be stuck here. In particular, if semi-classical gravity it has to be seen as nothing but an asymptotic expansion in g Newton or g h bar, then the story would end here and we can't go further. Okay, so that's why I'm sort of inserting this detour, the second part of my talk, where I'd like to argue that we don't have to think about semi-classical gravity that way. And in order to emphasize that, I'll give it a name. I'm hoping that there's something called exact semi-classical gravity. Okay, so what I mean by that is well, the starting point is actually a very old story, something we've done for half a century in many different papers. You take g to 0, but at the same time, you increase the number of matter fields, the number of species, c, to infinity, and you keep the product fixed. That's a nice limit. I think it was always popular because one thing it does is it suppresses quantum fluctuations of the metric. Okay? And it does that while keeping the dynamics of the theory interesting. Gravity remains dynamical. You can have a bunch a star can collapse and still form a black hole. When that black hole sits there, it will still evaporate in finite time. If you took g to 0 without taking c to infinity, that would not be the case. So the Planck scale in the strict limit really just goes to 0. So you have only one scale left, which is this species scale that is being held fixed. I'm going to call it the species scale. And that's, that has the dimension of area, so we have to take some root to turn it into a length scale. That's the only scale we get to think about now. And how we think about it, I think, is sort of crucial, and that's where I feel like Arvind Shahbazi's work from 2022 did a lot, I think, to change at least my perspective on this limit. The starting point here is to say, well, okay, here's the bare minimum that I think we can hopefully agree on. This species scale can be thought of as the scale at which higher curvature corrections to Einstein gravity become important. Again, the metric doesn't fluctuate, but Einstein gravity is not very useful on scales shorter than that species length scale. Okay. If we viewed this as merely a statement of an asymptotic expansion that cannot be resummed, then the story would end here. But the viewpoint that was emphasized by Arvind and that I think is sort of implicit in some earlier results, but I think wasn't articulated as clearly, for example, in many papers by Emperan and collaborators, is that we don't necessarily need to view this as an asymptotic expansion, that there may be an exact in CG theory that then admits such an expansion if you're interested in large distances. In that theory, the dynamics would be non-local on the species scale and below, because there are infinitely many terms here with higher derivatives. But again, the metric is completely well-defined on all scales. And semi-classical conjectures like the generalized second law, the covariant entropy bound, quantum focusing conjecture pertain to this regime. Okay. Now, this sounds like a fairly strong bunch of things to say, but of course we have an explicit realization of such a theory, which is a Randall-Sundam braneworld, in which we take the SUN, or I should call it here SUC for consistency, of super Young mills to infinity, while keeping the ADS bulk radius fixed. That bulk radius is exactly that species scale, and it realizes this limit. Arvind will discuss this, I think, in more detail on Friday, so I'll try to be very brief here. But the point is that this non-local theory from the brane point of view can still be solved by adopting the higher dimensional perspective and solving for the location of the brane in a higher dimensional ADS bulk that tells you exactly what the metric is on all scales on the brane. So these solutions are not just somehow obtained by doing an asymptotic expansion and you think you only know the metric at large distances, it's an exact in CG solution. And conveniently, we can also define the generalized entropy as an exact in CG quantity. Not as usual, like, okay, it's area plus von Neumann entropy plus higher curvature terms. We can just ask, oh, what's the HRT surface anchored to some region on the brane? That region could be very small compared to the species scale, for example. We can still ask that question. We get a finite answer, and that finite answer automatically resums this whole thing. Okay, so the generalized entropy defined through the HRT prescription is also exact in CG. In this setting, Arvin was able to prove a restricted quantum focusing conjecture, which is sort of the starting point for all other, everything that we care about. Well, the quantum focusing conjecture was a little bit stronger than what he proved, but it turns out that this restricted quantum focusing conjecture that he is able to prove implies all the things we know and love about semiclassical gravity. It implies the GSL, covariant entropy bound, entanglement wedge nesting, the QNEC, anything you want. It may even be the case that the original quantum focusing conjecture was false and that this setting taught us what the correct formulation is. The restricted quantum focusing conjecture basically says that the quantum expansion along a congruence along a null congruence cannot become positive. The original one said that it cannot increase. So clearly the restricted one it sounds weaker, but it turns out to be good enough for everything. Okay, so this is the setting that we're looking for if we want to prove a singularity theorem. And not just because it evades the dilemma that I described earlier. It evades this because we can start with a GSL, unlike Penrose, and so we can start with a solid starting point. And unlike Wall, we will not have to work in a perturbative expansion. We can do a non-perturbative theorem. But the other reason why this is a good setting is when you think about what it is that we're trying to rule out in the first place. We're trying to rule out bounces or baby universes forming in some sort of almost classical way inside a black hole. And if you wanted to make a claim that you have a theory with a bounce, you want to be in a regime that's like this, where you have control over the metric through the bounce. If you have some sort of strongly quantum regime where the metric fluctuates, that separates, say, a collapsing and an expanding era, you don't really have the causality structure available to claim that this one happened after that one and you had a bounce. Right? So you want to be in this kind of regime where you have good control over the metric. And so now we need to, of course, come back to this touching lemma, because that's going to be the bottleneck in the proof of a fully non-perturbative semiclassical singularity theorem. And there are two approaches that I'm aware of. One is mine, which I'll describe, and the other is to prove the original touching lemma non-perturbatively with improved tools, which is a recent paper by Arvin. So my approach involves a modified notion of trapped, and it came about because, well, for reasons I'll explain, I actually first sort of came across this modified notion of trapped as kind of the only way that you can define trapped in a sufficiently general way. And then it just turned out to be really useful for overcoming the limitations of the touching lemma. So let me describe that briefly. So this came out of work with Elisa Tabor, who is Jeff Pennington's student. So here I've drawn two edges of disk-like partial Cauchy slices. Very often in many of the proofs, when we think about entanglement wedges and their properties, we consider intersections of two wedges. Now, even if each edge was a perfectly smooth codimension 2 surface, the intersections or unions will have these sharp corners here. So these corners are generic. Moreover, we also often follow null congruences for a certain distance away from some edge and use that to define a new one. Those congruences have conjugate points and self-intersections that will also look like corners if you look at them on one-time slice. So we have to be able to discuss the notion of expansion that is so central to a lot of the analyses of these problems in a way that deals with these corners. Moreover, we learned, and at least for me this came again from Arvind's work on the restricted quantum focusing conjecture, which again says the expansion cannot become positive. And then that's good enough for everything. That tells us that we don't actually care about the value, the numerical value of the expansion for anything. We just care about the sign. So those two things together make it possible to define a notion of the sign of the expansion alone and nothing more. It's a very minimalist notion. Thank you. Which, continues to give you an answer when you ask what is the expansion at corners like this, and which is good enough for everything else. Okay. Let me maybe skip over this in the interest of time, but the work also helps clean up a proliferation of min and max and von Neumann expansions that had appeared, and turns out you only need max. Okay, so what are these signed definition of expansion that I'm going to need? Let me define future non-expanding first. Okay, so here's a little piece. This dark blue is a little piece of the edge of some wedge A. And here's a point P on it. And we'll say that the wedge A is future non-expanding at this point P if I can find an open neighborhood of P such that all outward future null deformations of the edge of A that stay within that open neighborhood decrease the generalized entropy, or whatever the appropriate thing for min and max smooth entropies is. So this is sort of the thing that corresponds to like quantum expansion being less than or equal to 0. But it continues to make sense, for example, at corners. Okay, and then it turns out that you also need a definition of some kind of generalization of positive or non-negative expansion. And you might think that you could just say, oh, if it's not FNE, then it's the opposite, but that turns out to be completely useless. And the concept that works, and that again was actually developed in a different context, we wanted to define the notion of simple wedges, the things that are not the Python's lunch, in arbitrary spacetimes, and we needed to develop this notion for this purpose, is past non-contracting and future non-contracting. So I should have said past non-expanding, of course, is just the time reversal of this definition here. And so now we're going to define past non-contracting and future non-contracting. Let me define past non-contracting. So this is a slightly more subtle definition where you ask, okay, here I have some region which has an edge which we know ahead of time is trapped. And trapped is going to be essentially the edge is compact and past non-contracting. So what makes this past non-contracting? What makes it past non-contracting is that I can find an open neighborhood of this entire edge in which it is impossible to then find an outward deformation like this purple one here. So these are future outward deformations, which has the property that it is past non-expanding on all new edge points. This outward deformation doesn't have to deform outward every portion of this edge. You're allowed to look for any, but I'm going to ask you to find one that is then past non-expanding on the new edge points that you generated by this outward deformation. And here this is impossible, right? This is a trapped region, and light waves are expanding in this direction because they're contracting in that one. This is usually how we think of as trapped. We're going up to the right, but of course that the same thing as saying that you're expanding when you go down to the left. Okay, so this surface here is past non-contracting because you cannot find any deformation which is past non-expanding on the new edge points. This surface here is not past non-contracting. You can just go up this way. These light rays are contracting towards the past, so you can find such a deformation. Okay, sorry for the convoluted definition, but it's the only one that I think works for other applications, not just the singularity theorem. So here's the promised definition of trapped. It means P and C, and the edge of A is compact. So same examples, right? We would now say that this is trapped. Interestingly, by this definition, the surface that lies exactly on the black hole horizon, which would not be trapped by Penrose's definition, and in fact, these light rays do not hit a singularity, right, is trapped by this definition. And here's the statement of the and the proof of the new singularity theorem. Okay, so we again start with an extendable globally hyperbolic spacetime containing a trapped, in the new sense, a trapped wedge with Cauchy slice sigma A, shown here as usual in blue. We're going to assume that this is a non-compact slice, and then M is singular, assuming the GSL, of course. Okay. So more specifically, what exactly is singular? Now, it's not necessarily the light rays coming out of the edge of A, of sigma A, that are going to hit a singularity, because that edge could lie on the horizon here. It's the light rays coming out of deformations of A that are going to be shown to be singular. The assumption that A is trapped tells us that there exists an open neighborhood within which we cannot find a deformation that is everywhere P and E. So what we're going to do now is prove that if there was no singularity, then you could find a deformation that is everywhere P and E on the new edge points. So first of all, this outward deformation, of course, is also non-compact. So it again follows that its future Cauchy horizon cannot be compact. So as usual, it follows that there is at least one, if we assume for contradiction now geodesic completeness, then there must be at least one light ray that stays on the boundary of the Cauchy development of sigma A forever. And as usual, it connects a point P to some point Q on future infinity. And we can define a causal horizon that meets the edge. So in this space-like picture here, A is the shaded blue region, B is bigger, right? But because it's the exterior of this red line, of this red sphere, it's all of this. The interior is sort of the complement of B. And this causal horizon is going to touch the edge of B at one point in general, P, and it'll be connected by an infinitely long light ray to some point on future infinity. And now we'll use the GSL to argue first that, of course, the quantum expansion of C is such that generalized entropy has to increase towards future infinity, decrease as we go back. In particular, it means that C is everywhere past non-expanding. That's the statement of the GSL. Things have to shrink as you go towards the past along the causal horizon, sort of intuitively, right? Now, C itself doesn't help us yet, but what we can do is define a new wedge or a new region that's the union of A and the exterior of this causal horizon. So we don't just have this blue shaded region, but we now also have the pink region in that union. And that union can be viewed as another outward deformation of A. Remember, we got from A to B by doing this outward deformation. This is a smaller outward deformation of A that doesn't give us all of B. It just gives us this pink region. But by strong sorvativity, on all the new edge points, which is this sort of arc here that bounds the pink region, these are the old edge points of A. But all the new edge points are part of the causal horizon. And by strong sorvativity, since the causal horizon was P and E, they are also P and E. And so we have found precisely the kind of deformation that the P and C assumption, the trapped assumption for sigma A, said should not exist. So that's the contradiction. And it's also the end of my talk. Thank you.
So this is intended to be a very generic singularity theorem, generalizing Penrose. But Penrose had two non-unphysical assumptions, right? The null curvature condition and global hyperbolicity. What are you doing with the global hyperbolicity?
Oh, I'm going to assume it. Yeah, I don't know what to do about that. Yeah, right. So I think a very interesting problem from my point of view would be to try to. So I'm glad that people are working on the endpoint of black hole evaporation, and it's like it feels like the right time to turn to that problem. And I think it might be nice, and maybe I'm naive about expecting progress there, but if you could use this exact semi-classical gravity setting, for example, specifically the RS setting, to try to study the endpoint of black hole evaporation, that might be very interesting. We might learn something about, exactly how we should think about the resolution of these violations of global hyperbolicity that we would expect there.
Yeah, cool. When you move away from this exact semi-classical limit and reduce the number of species of fields and turn on quantum metric fluctuations, does the argument or the potential argument about the resummation of the singularities to give something non-singular still apply, or is it ruled out by this zero-order argument?
Yeah, so if I understand correctly, you're asking like what about the real world? Maybe in the real world we don't have infinitely many species, and so how far does this get us? And I think it gets us. I mean, the extent to which this becomes an approximate statement and not as reliable as before is sort of precisely the extent to which the metric now fluctuates. In many real-world situations, of course, we're not super worried about huge quantum fluctuations of the metric, but in principle, we could be worried about it. And it's also exactly the extent to which a claim of a bounce becomes less well-defined. So I feel like to the extent that we view this as a sort of conflict between, wanting to say that there's a bounce and wanting to say that there's definitely a singularity, both of the opponents are weakened in equal measure when we leave this idealized setting.
In your entropy formula, in the higher curvature theory, why isn't the Wald-Donk formula applies, and instead you just have a Bekenstein-Hawking entropy formula?
Are you asking why HRT works?
Where you have CG as the length scale, CG to some power. You would expect in such a theory that the Wald-Donk entropy formula would capture the entanglement entropy. But instead, your formula showed just the Bekenstein-Hawking.
Oh, that was just there were dots. There were dots, but yeah. So it on large length scale, those dots are small corrections. But the more central point that I think I'd like to advocate is that we can think of applications of the HRT formula in a Reynolds-Sundin braneworld setting with SUC, C goes to infinity, as computing just a resummed version of that whole thing. And so you just get directly the full answer, and it makes sense at distance scales that are small compared to the species scale, for example. But the expansion would be completely useful.
I have a question about the Randall-Sundrum discussion.
Yeah.
In the end, you're considering a classical theory in one higher dimension. So
Yes.
through these theorems you're discussing reduced to the usual classical, let's say, Penrose theorems or singularity theorems in higher dimensions.
I have not thought about that at all. That seems like a really great question. Yeah, I don't have anything to say on the spot, but that seems worth thinking about. Thanks.
Thank you.